But hello, everyone. I'm Paul Ricketts. I'm the director of the South Physics Observatory and the Department of Physics and Astronomy's outreach person. I always forget what they call me, the interpretive specialist. Yeah. But yeah, anyway, that's me. I'm here with Dr. Nolan Matthews. He's a recent PhD graduate from the U. He's been working with one of our professors, Tugdual Lebowick. We did a talk with him a little while ago about some of the work he's doing with gravitational waves. But Nolan is working on another aspect of something he started, and it's called intensity interferometry. So I'd like to welcome Nolan. Right now, he's no longer in Salt Lake. He's slowly bouncing around the country on his way to France, right?
Mm-hmm. That's correct.
Yeah, to continue his work in this field. So, yeah, you want to talk about yourself for a second? Let everybody know where you're coming from right now.
Yeah, so I was a graduate student, and I worked with Tugdual Lebowick, but my actual advisor was Dr. Ejecta, and working on this technique of intensity interferometry. The main idea of what we were doing was to try to enable a technique that can help study stars at a very high resolution. We essentially want to know, the sizes of stars and understanding stellar physics and stellar evolution. And so I worked on the instrumentation side of things and also participated in observations and the whole gambit. I'm not sure exactly where to go from there. I'm currently working as a postdoc with Dave still. And yeah, like Paul said, bouncing around the country, currently in Houston and just getting over that crazy winter storm that hit Houston. On my way to France to continue working in intensity interferometry.
All right, cool. So I'm going to have to mute while you talk because there's always an echo while you talk.
I see.
It's something I haven't been able to figure out how to take care of yet. But
technically.
So I have some questions. If there's anybody that is online who has questions while Nolan and I are talking, feel free to ask them in the comments. And as soon as I get a chance to ask them, I will. So, if you're coming through and you're not understanding anything that we're talking about, feel free to ask, and either Nolan or myself will try to interpret it into a much easier way to talk about it, because intensity interferometry is not an easy subject, as Nolan has learned while working on this. But I've got some questions, and so... my first question is basically just how did you choose physics as your career, and what was your path like to get where you are? And this is like kind of a question for maybe budding astronomers or physicists that want to know like the path that they could follow or other people's paths, and kind of give them an idea of what they can do when they start getting into like an undergraduate or even into a PhD. So yeah, go ahead.
Sure. Yeah. So my interest in physics and astronomy, I think started at a pretty young age. I had a pretty inspiring high school teacher, and he was just very excited about doing lab experiments. I remember doing the single slit and double slit lab experiment with tinfoil and a laser, and that kind of spawned my interest. And so I went to the University of Maryland for my undergraduate, and after that, kind of working with my high school teacher, or at least being in his class, I really wanted to do physics. I also thought about engineering and other things, but I just felt like physics was, really addressing like sort of fundamental questions about the way things work. And I also found that it gave me a broad platform in which to say maybe I didn't like physics so much, but it gave me a base to say maybe pursue engineering or something maybe a little bit more applied. So that's kind of how I just got interested. When I was at University of Maryland doing my undergraduate, I doubled in physics and astronomy. And I always had interest in astronomy from very early on with the Cosmos series by Carl Sagan, and just wondering what's out there, what is in the universe, how does it work, and just these big questions, and so approached astronomy as well. And so after my undergrad, I participated. I think the really thing that kept me going in a career in academia and staying in physics and astronomy was kind of participating undergraduate research. I worked with a couple professors in actually studying exoplanets, and then one other one doing gamma ray astronomy. And that kind of experience and research I really enjoyed, and kind of made me learn that research is something I wanted to do. And so with that kind of feeling, I ended up applying to a bunch of graduate schools, didn't get into a bunch, but got into a few. And after visiting Utah and seeing the really cool department and growing department, as well as spending some time in the mountains, I was like 100% convinced to come here. So I ended up coming here for graduate school to Utah, and then where I got involved with the work with Dave Kita and Tugdual Loboic on intensity interferometry. So that's kind of I guess the long story short is, they just early on was interested in physics and just kind of kept scratching away at different layers of it and just continue my interest in it to where I am now.
Yeah, I would think you're kind of an avid outdoors person,
yes.
So this is a good fit for that.
A big draw, yeah. Big draw. Yeah. I remember visiting Utah and going snowboarding at Brighton and was just 100% convinced.
Yeah, well, that seems to be a common point for a lot of people. Cool. So, so you seems like you did a couple things before jumping onto this, but that's cool that you finally got here and made something from that. But yeah, the department is still growing. We're actually, I think, thinking of hiring some more astronomers within the next year or two. So it's like, and then I think we just hired even a few more physicists this last year or two. So it's like it seems to be constantly getting more and more stuff.
Absolutely. The thing I was going to say was the thing that drew me the most was, of the schools I got into, I always saw at least one professor that I thought I could work with and a project that looked kind of close to my interest. But oftentimes there wasn't more than one or two. Whereas at Utah, there was just so many people like Anil Seth's work, Kyle Dawson's work, as well as the work with intensity interferometry. I mean, it was just so vast. I could really see myself in a couple of different areas, and that was another big draw for me. Was just how the strong the astronomy department was.
Yeah, it always seems like our professors are kind of like looking for people to come and to help them with their research and stuff. So that's always a good point. And I guess there's always a good flow of research money coming into things because they're always like doing stuff that are like, I've never heard of this kind of thing. So yeah, that's a good point. So my next question, well, actually we have a couple comments. One is Robert. I think we can answer this as we talk, but he says, I've used an interferometer microscopic leveling. How does that shadow bands relate to astronomy? So I think that might be answered a little bit later on.
So I missed the interferometer.
He says, I've used an interferometer microscopic leveling. How does that parentheses shadow bands relate to astronomy?
I'm actually not sure what that is. It sounds like maybe an applied technique for like condensed matter or something. Maybe if there's some follow up there. The core idea of interferometry, the core word is in the word interference. It's the idea of using the interference between waves, light waves, sound waves, something, to draw information from the thing that you're looking at. Sometimes you probe something with, say, a laser or something, and based on some sort of interference pattern you get back, you can draw information from that, say like on small materials. But then also things that emit waves, things like stars, you can use the interference effects of those to also draw information, say spatially, spatial information about the surface of the star. And so in the core interference, it's at least to my naive understanding of what interferometric microscopic leveling is. I'll just say that broadly.
Yeah, I'm not sure either. I've never heard of that. But if Robert wants to expand on that on the next comment or something, we might be able to talk about it more. But Tugdual is watching. He posted that interferometry is everywhere, and that's.
Yes, I've shared a few discussions with him on that, and it's just ubiquitous. You see it in LIGO, for example, which is just the most precise interferometer ever built, which measures gravitational waves to astronomical interferometers, which work both in the optical and in the radio. You have interferometry for studying very small materials. It's used so widely. It's really an amazing technique.
Yeah, and it's literally everywhere. Even, I don't know. I think personally, your brain does a little bit interferometry between your eyeballs.
I think
Sometimes.
also, I think a really, I should have mentioned this, but an interesting YouTube series are the interviews with Richard Feynman, where anybody who hasn't seen them yet, who's interested in physics, should really check them out. And he said something a long time ago, which I didn't really understand, but he was talking about, the idea of dropping a bunch of pebbles into a pool. And then you can imagine a bunch of flies being on different parts of the pool. And if those flies could talk to each other and they could see how each one is going up and down based on the interference or how each one of those flies is riding those waves, you can actually figure out which pebble was dropped and where. And that's just another, idea of this idea of interference. And I just found really cool to think back upon.
Yeah, that seems like an interesting point. It looks like Robert has posted a link to a PDF. Probably read that in a minute, maybe. But yeah, I guess we'll move on to the next question, and that's basically just, how did you come across intensity interferometry as a research subject, and what about it drew you in?
So intensity interferometry and interferometry in general, I didn't have really any experience with it other than in my coursework at the undergraduate level. The first time I actually read about it was when I was visiting Utah to see if it was a school I wanted to go to. And I read a couple papers led by Tugdual and his student, Paul Nunez, which spoke about these, impressive high resolution capabilities of this intensity interferometry technique. And so reading those papers, it just seemed like a really cool project. And when I arrived at the university, Dave Keita had kind of taken it over, and he had this vision for this digital approach using digital electronics to record the starlight. To help with the characterization of the star at high resolution. So that's kind of how I first sparked my interest into it. But the thing that really drew me to it was the project. It wasn't just working with data. It was a really hands-on application where first couple of years I was working purely in the lab, developing the instruments that would eventually go on to the telescopes that we're using now. And so I found a lot of interest. My background is in physics and astronomy, and so doing instrumentation for telescopes is just something I find really enjoyable. It's a nice synergy between the two, and being in the middle is nice.
That's cool. Yeah, it's interesting how people get into research sometimes. It's just like I've talked to some people, and they're just like, I don't know, I just came out of nowhere.
Yeah.
I thought it was cool or something, or
Yeah.
had a thought or something.
Mm-hmm.
Cool. All right. So let's talk about intensity interferometry now. So we're going to start at the beginning. Where did it start, and what about it took so long to get to the point where you are right now?
Sure.
Because it's been around for like 60 or 70 years,
Yeah, absolutely. Right? Yeah, it has. So the technique was kind of born in the 1950s with some ideas. Robert Hanbury Brown, and he had these ideas for intensity interferometry, which he used for a radio telescope, and he eventually took it and applied it to optical telescopes. And these ideas ended up leading to the construction of what was the Narrabri Stellar Intensity Interferometer, which was this 2-telescope interferometer in Australia. And at the time, this was a really breakthrough instrument. They used this Narrabri Stellar Intensity Interferometer to measure the diameter of 32 different stars, which at the time was just unprecedented. There were only 6 stars prior to that experiment that ever had their diameter actually measured by Michelson, actually. And with this intensity interferometer, it just really broke into a new field. But the problem was that at the end of the operations of the Narrabri intensity interferometer, it kind of observed everything it could in the sky. It was really restricted to really bright stars, brighter than a magnitude of about 2.5 in the visual band, and that was something. It was all 32 stars that was observable by them were observed. So essentially, they just did all they could. And at the same time, at the end of that experiment, there's some breakthrough techniques in amplitude interferometry, which is the technique most used today in astronomy by Antoine Laborie. And with those, they achieved something like a factor of 40 times more sensitive instrument, with much smaller telescopes. And that field kind of took off, and intensity interferometry was kind of left in the dust. And so what happened was, it wasn't like it was continually developing all this time. It just, all the breakthroughs in amplitude interferometry continued to grow, and that was the preferred technique. But what was realized, and this is largely spawned from like Tugdual, his ideas of using imaging air shrink off telescopes as intensity interferometers, and maybe we'll go into more detail about shrink-off telescopes later, but there's the idea that there's these large arrays of many telescopes with very large diameter being built, and in fact, they can be used for intensity interferometry. And this spawned some extra interest. There's for example, collaborators in Sweden like Dennis Dravins, who kind of also work to explore the potential of these arrays, and eventually realized the sensitivity limits that kind of held up Hanbury Brown a long time ago weren't as, were new now. Like essentially you could see much fainter stars than what were observable to Henry Brown. And that kind of realization has now spawned a bunch of interest. And so a lot of groups worldwide have now picked up the technique, us at Utah being one of them. And that kind of led to my formation of my thesis project, which was the development of an intensity interferometry instrument. Hopefully that answers your question some part.
Yeah, no, you did it really well. So yeah, that was a good background for it. So yeah, so Michelson interferometry kind of took over the field for interferometry for the longest time. And so, yeah, I guess.
And I would say still is at the moment. It's still an extremely powerful technique. But there's pros and cons to using amplitude interferometry versus intensity interferometry. And maybe we can get into these details later, but there's very...
Yeah. Okay, cool. So now that we know where it came from, let's talk a little bit about it. It's the theory behind it. This is going to be kind of like the harder part because a lot of people may not know some of the physics behind it, but let's give it a try, and we can, just kind of work with it as it goes. So, yeah, just start wherever you want.
Sure. Yeah. And so here I'm gonna share my slides. And so hopefully it gives a more visual illustration of what's going on. Hold on a second here. Share screen. Okay, so you see that slide well?
Yeah, looks good.
Okay, full screen. Okay, and so the basic idea of an intensity interferometer is if I can actually maybe go back just a little bit, it's the idea of using multiple telescopes in combination to form a much larger telescope. Essentially, the resolution that you can attain with a telescope is given by something called the Rayleigh Criterion, which is the angular resolution you have is something like the wavelength that you're observing at divided by the diameter of the dish. So if you have a really big diameter dish, you can observe smaller and smaller features. The problem is that if you look at stars and their typical diameters, or at least expected diameters, you see that most stars, what you would actually need is dishes in optical light of something like 100 meters, so like a football field in size, to actually resolve the surfaces, to get an angular resolution that's at say even just measure the diameter of the star. To really start to see the features of stars, you need to have a diameter of the telescope something like up to 1 kilometer, which is just, you're talking about 1 kilometer optical telescopes, and it's just not practical. And so interferometry is very useful because what it allows you to do is use 2 telescopes in combination, where now the angular resolution of these 2 telescopes working together is something like the wavelength divided by the distance between them. So now it's much more practical. You can have 2 telescopes separated by 1 kilometer or 100 meters, and you essentially get the resolution at those scales. So that's the main thing, is that to really get to resolution to see these stars, you need interferometry to do that. Now, getting back into the technique itself.
Can you go back to that slide for just 1 minute? Because apparently it was cut off a little bit, so I want to give people just a little bit of time. So before the right-hand side was cut off, so you couldn't see the graph that you were talking about.
Okay, so is it better now?
Yeah, I fixed it because it was just it was coming in weird.
Yeah, so I can briefly explain. Again, it's just the angular resolution that you have is something like the wavelength divided by the diameter of the telescope. And so to see smaller features, you need bigger telescopes. And what this plot is showing you here is the number of stars for a given diameter. And this is a unit is measured in milli-arcsecond, which is a very, very tiny angle. And the main point I'm trying to get across is that if you were to use a single telescope and you wanted to resolve the surface of a star, for most stars where this plot picks up in number, you need a telescope that's something like 100 meters up to 1 kilometer. And so you're never going to build a single telescope that big. And the idea is that you can use multiple telescopes separated by those distance, and by having them talk to each other in some way, you get a resolution back that is instead of the wavelength divided by the diameter like it is here, it's the wavelength divided by the distance between them. And that's just the main idea, is that, you want to resolve stars, you need big baselines, big separations between the telescopes to do so.
Yeah, and so when you talk about putting them together, that's either optically or electronically. Or
exactly.
Something.
And so the original interferometer, this was from Albert Michelson, it physically combined the light together. And so what he had was a series of mirrors that essentially would collect the starlight, and through these optics, these mirrors would actually bring the light together. He also had some kind of creative ideas about how to correct for atmospheric turbulence, which he at that time did effectively by hand, which is just unbelievably impressive. I think looking back, essentially it took something like 60 years from this original instrument for amplitude interferometry to be used again in astronomy. But again, the idea was that he had these series of mirrors, and by separating the distance of these mirrors, these first two mirrors here and here, he could change how the interference pattern that was formed when the light was combined. And so essentially by varying that distance over some scale, it actually probes the size of the star. And so this is direct interferometry, or amplitude interferometry, where the light is being physically combined. Then, so this was in the 1920s. Then in the 1950s and 60s, with the publication finally in the early 1970s, was the development of the intensity interferometer. And this was that instrument I was talking about earlier, the narrow stellar intensity interferometer, which was these two telescopes here, which were stationed on this giant circular track. And each one of these telescopes were 6 meters in size. You can kind of see a horse here for scale. And what they would do is that these telescopes could be positioned at different distances in the same way that Michelson uses two mirrors at different distances to essentially probe the coherence, or essentially the interference effects of the star at different scales. And so they were not, the light here was recorded electronically. And so the starlight was turned into a current. Essentially, he turned the light intensity from the star into a current, and then he had an electronic correlator that correlated the two currents. And based on how they were correlated, you could retrieve back the information about the star.
And so what would a correlator actually do? Does that just time the path lengths or something?
So the correlator just measured so you can imagine having two signals. It measured the cross correlation between them. Essentially, you can imagine, so this actually goes into, I think, these slides here and maybe I'll just take a step back with this kind of illustrative example, is that when you think about intensity interferometer, what you do is you record the starlight intensity at, say, 2 different telescopes with some separation between them. And what you see is that if I was to say record the intensity at different distances away, so B equals 0 means the telescopes are right on top of each other, B equals 0.5 lambda over theta is some distance away, and I'm increasing in distance. As I increase in distance, the currents that these two stars these two telescopes are recording are going to start to decorrelate. When they're on top of each other, of course, they're going to see the same signal. As you go to larger and larger baseline separation between these telescopes, these two intensities start to decorrelate. And what I mean by cross correlation was if I was to say correlate this blue line with this black line, and I was to shift one of the signals back and forth as a function of the relative delay between them, what I would get is that at 0 time lag, I would get an excess. And then at larger time lag, when I shift away by some amount, I get essentially no correlation. And the amplitude of that correlation at 0 time lag tells you is you're starting to draw information from the star itself. And this goes into the last point, which I'll make here, and I'll just say is that if you measure now this amplitude, how correlated are these two as a function of the distance between them, this is directly related to, say, the size of the star or spatial features of the star. So you're seeing how these intensities correlate, and based on how they're correlated, you can draw back information from the surface of the star.
So how closely do you have to know the positioning and the timing between these?
So for amplitude interferometry, it's a fraction of a wavelength. Because if you go more than a fraction of a wavelength, the interference effects between the two light paths will essentially lead to destructive interference. For intensity interferometry, it's a little more subtle point, but it depends on how fast you record. And so for example, in our case, let's say we're recording at every nanosecond. So light travels in a nanosecond about 1 foot. And so our path length, or the essential tolerance to mechanical fluctuations, is something like 1 foot. And And that's way, of course, way bigger than say for amplitude interferometry. And that's one of the pros of this technique, is that things like atmospheric turbulence, where these path lengths, the light to each of these two telescopes are fluctuating, it doesn't matter so much for when you're recording at these rates. If that makes sense. Essentially set by the electronics is how fast you record. If you record really, really fast, then the tolerance becomes smaller and smaller.
So let's see. Is there any more of the theory that you would like to explain before we move on a little bit more?
No, I mean, the only thing I'll talk about or mention is I think this was when Henry Brown was doing this, and this is something you and I just talked about before the talk began, is that when Henry Brown was doing this idea of whether the light could be correlated to optical wavelengths was hotly contested. Essentially, when you break it down to a quantum picture for, and I should have had a slide on this, but it essentially was the first. I mean, it's considered as one of the first tests in quantum optics, which led to the idea of what's called photon bunching. And so these correlated intensities, I don't know how it gets a little technical. I wish I had prepared a slide on it, but essentially this is, this technique, which was used for astronomy, was actually one of the first tests in quantum optics and a demonstration of photon bunching, which is a very, interesting quantum optics thing.
Is that similar to, I just read something that's related a little bit more towards gravitational wave astronomy, where they were looking at a new type of advancement that uses phonons.
So I've heard of the idea of squeeze states. I don't want to speculate too well on here, so he could probably tell us better about these things than I could.
But is the idea with the photon bunching similar to the idea of what they were talking about with the?
So the thing I want to illustrate is that you can have, the way it was demonstrated originally was in the laboratory. You shine this thermal light into a beam splitter, which divided the light into two. And now for waves, there's no problem that light gets divided into half the intensity goes one way and half the intensity goes the other way. Now, when photons are bunched, if you have no possibility of photon, and you think at the quantum scale of individual photons, that means when a photon arrives at the beam splitter, you have one photon going one way and one photon going the other way. And because they're discrete, if bunching wasn't a thing, essentially that they would always be decorrelated. Whereas if they're bunched, then you can have a pair of photons, say, and then they get split equally. One photon goes one way and one photon goes the other way, which leads to a correlation within the time scale that these photons are bunched. And so that's when they did in the laboratory, that's the technique, is you divide the light into two, and you can see that within a small time scale, you have this excess correlation, which is the photon bunching.
Okay, so it might be a little different than what I was thinking. Okay, anyway. So let's talk about this related to other types of interferometry, because there's Michelson interferometry, but there's also interferometry that radio telescopes use. And is this similar to the radio telescope interferometry and completely different than Michelson interferometry?
So I would say the radio interferometry, the advantage that they have, I would say it's different than what they do in radio interferometry, because in radio you can record you have light, which is, wavelengths are on, human scales, essentially centimeters to meters. And you can actually record with fast electronics, you can record that electromagnetic field you get the amplitude and the phase information. Whereas in optical light, I think you would have to record at like terahertz frequency, faster than terahertz frequencies to be able to record the amplitude and phase. So you cannot do that in optical light. And so in optical light, that's why amplitude interferometry they actually physically combine the light. But it is close to radio interferometry in the sense that we digitize locally at each telescopes. So we record the intensity at each telescope and then correlate after the fact, which is very different than Michelson interferometry in astronomy.
Yeah, you can't correlate after the fact with Michelson, right? Like at
You have
all,
to do it
because
in.
like if you don't get it right there, then it's completely lost, and there's no signal or anything that you pull from.
Yeah.
Okay, so that's kind of cool because then you can like record everything. I was reading on some of the stuff that you can record things from possibly different telescopes in completely different locations, and as long as you have the timing correlated properly, then you can bring the signal back together, and so then you can have really long baselines. Is that did I get that?
So that's similar. Yeah, exactly. And I think that's a huge advantage of this technique is that, you can scale to many different telescopes. Not only have telescopes in remote locations, but you can have, 10 telescopes. And as long as you store the starlight intensity information at each one of those, then after the fact, you can go in and cross-correlate between all of them to get the information about the star. Whereas in amplitude interferometry, you have to physically split the light for every other telescope. You have to split the light to combine it with some other telescope, and then at a certain point you start to run out of light. So that's a drawback. But again, the other fact of that is that the sensitivity is much higher. So it's in amplitude interferometry. So there's trade-offs there.
Yeah, I remember I visited the Chara array, which is the Michelson interferometer, and I think they use 6 different telescopes at different baselines. And I saw their I guess their optical correlator, which is basically like these giant long tracks where they have to like put mirrors on there, and they have to have them at like super precise distances with each other, with all different 6 of them. And if like one of them wasn't right, then it would like throw everything off. And so it was like extremely difficult to get, that many telescopes to read properly. Whereas this, it would be a lot easier doing that kind of thing because you don't have to have those like long distances and stuff like that built in.
Exactly.
That's cool. That seems like it would be a little bit easier. And so that's
mechanically
that's why
and much less.
And so that's why it's like kind of an idea to use these Cherenkov telescopes that are being built, because they're supposedly doing like how many is proposed for one of the next ones?
So for example, let me share my screen again. Let me see where I was. Yeah, so this you can see the slide well. Okay, cool. So these are Cherenkov telescopes, and so maybe just a bit of background is that these telescopes, they're different than like the conventional optical telescope like you have at the South Physics Observatory, in that they're made up of many different segmented mirrors, and they're and the other thing is that they're extremely large. But the purpose of these Cherenkov telescopes are actually for gamma ray astronomy. They image these faint flashes of light that happen when a gamma ray photon interacts with atmospheric nuclei, creating these Cherenkov showers. And so these giant, optical like telescopes are used for gamma ray astronomy. And so, but to see these showers, you have to make them really, really big. And so you were asking about the numbers of telescopes. And so, similar to us, they're doing this. They need large amounts of telescopes. We need it for kind of characterizing the star in many different angular scales. They need it for kind of this stereoscopic way of viewing this Cherenkov shower. But anyways, these arrays that currently they're, for example, the one we work with in Tucson, Arizona, VERITAS, is an array of 4 different telescopes. And these 4 different telescopes provide you 6 independent pairs, or 6 different angular scales that you can characterize the star at. Whereas in the future, this is an artist's impression of the future Cherenkov telescope array, which will be there will be 2 sites, one in the northern hemisphere and one in the southern hemisphere, and these will consist of 15 to 20 telescopes all the way up to potentially 100 if the full array is built. And then this would be unprecedented in terms of the interferometry capabilities, and you could imagine outfitting each one of these telescopes with an intensity interferometry system.
So you would build like a whole correlator system with the recording system on each of the telescopes instead of having them at a common point, and then you would like later add all that later, or would you have to have all of those in a common point for the signals to be brought in? And then recorded?
There's 2 approaches to this, and I think it just depends. It gets into kind of technical questions. The idea is you could, for example, record the starlight at each telescope independently, and then after observations are over, you correlate them and you extract that information about the star. But the other way you could do, like radio interferometers have very sophisticated electronics, and they're able to do the correlations. For example, like ALMA is able to do the correlation between many, many telescopes in real time at very high frequency. And I think a professional system like on CTA, you would want something more, maybe more in real time than dealing with 50 huge data files. But
so would that come down to like using a GPS timing signal and stuff to get everything properly located and properly timed in order for you to be able to build that back?
So I think, I don't know exactly the approach you would take, but the positions of the telescopes are, you need to very carefully know the positions of the telescopes. You need to know any sort of time delay that exists in one telescope versus another. And all these calibration metrics are being built into shrink off telescopes because you need them for gamma ray astronomy as well. So I think the intensity interferometer could benefit from that. So in essence, I'm just, the time delay could be measured. You just have to measure it very carefully at each telescope. And once you know it, then you can compensate for it after the fact in the analysis.
So I've got two questions. One, like the optics on these telescopes don't need to be like a normal telescope optical quality, right? They can be kind of like a little bit less flat or a little bit less curvature.
The point spread function of these telescopes, it depends a bit on the size and the exact optical design of the telescopes. If the point spread function for these telescopes is something like 0.06 or 0.1 degrees, which compared to an optical telescope, which at the seeing limit is just, it's like 100 times better. And so they're really, in terms of optical quality, they're quite crude, but the trade-off is that you can build these telescopes very, very large, which is the most important thing for the signal to noise, the sensitivity of the intensity interferometer.
So when you're taking the light data from your objects, like what are you using to actually grab it and how are you using it? Like, it's not like a regular astronomy camera where like you have something pointed and it's just like taking in light and kind of building it up into pixels over time. How is it different?
Right. Yeah. So that is an important distinction. And so I can just show a picture here. So this is the VERITAS array near Tucson, Arizona. And what we do for intensity interferometry observations is we actually put this plate on the telescope, which is actually in front of the gamma ray camera. And this gamma ray camera is a ton of individual detectors, like something like 400 individual detectors that they use to image these strength of light flashes. But during our time on the telescopes, we can kind of mount this plate on the front of the telescope, and we use this mirror here, which redirects the light from the main mirror of the telescope into this photomultiplier tube. And essentially what this photomultiplier tube does is convert the starlight intensity into an electronic current. And so if you have a higher current, that means you have higher light intensity. And the benefit of these photomultiplier tubes is that they're very fast. They can operate at nanosecond timescales.
So it works continuously. It's not like it takes one picture for like 10 minutes, then downloads it. It's like a constant download. And so the faster it downloads, what can you tell with faster, like a download speed and stuff like that? Like if your system is faster, is that any better?
In a extended way, like so the main idea is that the sensitivity, the faster your light detector is, the higher sensitivity that you get. And so that's the main thing, is by having a faster detector, you're able to just have a slightly higher sensitivity. But you're right, you still need to integrate over, say, something like half an hour to hour periods to get enough data to build a signal, because it's a very small effect that you're looking for.
So instead of like building it all into a circuit that gets downloaded, you constantly read it out and then build it up on like a data file later to be.
So that's what this second photo here is that the starlight intensity, which is recorded as a current from the detector, is then sent to this very high speed data acquisition system. And what this system does is essentially record the starlight intensity every 4 nanoseconds and just pushes it to disk. And this is a very data intensive process. We, in a single night, we'll get something like 12 terabytes of data. But the idea is that at each telescope, we store the starlight intensity. And then after the fact, we have a correlator which processes these something like 40 terabytes of data that we collect a night.
So you're spending like $500 on data storage a night.
Say that again. Say that again.
You're spending like $500 on data storage every night.
I guess the systems to be able to read this fast, you know, you can have like hard disk drives, which are not too expensive, but to be able to read this fast at 250, we read at 250 megabytes per second, and so those are a little bit more expensive, but you're right.
Yeah, that would be like in terms of like a newer SATA drive or something like that, right? That you'd have to constantly write that onto.
Mm-hmm.
Okay, that's cool because that gives a little idea of how it's like different. Like it wouldn't be super easy to do this like in somebody's backyard,
right?
Because of like because of the electronics, basically.
Mm-hmm.
Okay.
Yeah, it requires a little bit of a sophisticated kind of instrumentation. Yeah. So one day, I think maybe we can have over-the-counter intensity interferometry setups for amateur observatories.
Everybody just throw in some data every night at the same star and have like a giant network of these, right?
Yep.
So the size of the telescope matters too, just because that allows you to get a brighter signal from the sky, right? So that's why
the size of the telescope.
Yeah, the size. That's why, like you initially started out at sea base using how big were those telescopes there?
Those were 3 meter diameter telescopes.
3 meter. Mm-hmm. And so then, but that wasn't giving you a clear enough signal,
right?
And so you went to VERITAS, which is 12 meter. Mm-hmm. So that's like a directly correlated with how much light you get is how much signal you get, and that comes back with how much integration time and stuff that you can see, right?
Yep.
And does that also help you with determining how fine of a detail you can see? Like,
yeah. So I was just going to say, with larger telescopes, you can observe with less time for the same signal, but if you observe with longer time, then you get a really strong signal. And to be interesting, I think you need to, say for diameter measurements, which is I think the first measurement you make in astronomical interferometry, you kind of want to be measuring stars at the level of a few percent or better in terms of their size for this to be scientifically interesting. And to do that, you need so these larger telescopes are essential for getting down to that level.
So what determines how small of an angle you can actually resolve? Where does that determination come?
That goes back to the baselines between the telescopes. Essentially, if you have larger and larger baselines, you can see smaller and smaller features, or smaller and smaller stars.
So you would basically need fairly large telescopes at fairly large distances apart. So it'd be something like you'd have to build a system that's similar to like a radio interferometer in that kind of idea of what it would look like. So like the VLA in New Mexico, that would be something ideal for this kind of thing.
Yeah, I'm not sure the spacing, but exactly that. I mean, when you look back at this picture of, I think I'm still sharing my screen, right? Yeah. If you look back at this picture of CTA, you can just imagine, this is like the optical, it's an optical array of telescopes and something like that, which would, I think, in some sense, it's just an array of telescopes, but this is what you need: telescopes at many different separations to characterize a star over many different angular scales. You're going to get the highest resolution from, say, the telescopes that are separated the farthest, but you're going to get the best signal, say, from the telescopes that are the biggest.
So one thing I didn't ask in the previous questions that I sent you, but it's something that I thought of before. What is the chance of seeing like transient effects across like the surface of a star, like a sunspot or something, or maybe a planet crossing or something? Is there a chance of seeing that kind of thing with this?
Not with the current system. I think you can, if we were to take all the advances in intensity interferometry, there's ways to push the sensitivity. You can get to the point where I think, seeing something like star spots, it could be a realistic possibility. And this has actually been, let me skip forward. This was work that was done by Paul Nunez with Tugdual Leboeck and Dana Stravins. And he showed that, he used a CTA. This was done before a CTA, like this specifically with the properties were known or the parameters of the telescopes were known, but he used a CTA-like observatory. And these simulated observations actually showed the capability to recover stellar surfaces with hot or cold spots. And so I think that is a true possibility.
I was reading in there. There's also a thing about the temperature of a star. Like if the temperature is too low, does that just come from just like how much light output it has? So like if a temperature of a star is too low, it doesn't have to do with the temperature, but more of the light output. So that's why you kind of focus more on bright bluer stars.
Yeah, so it's there's a couple things that goes into the temperature. One is kind of goes back to this photon bunching effect. Is essentially when you have higher temperature, this photon bunching effect is enhanced, and so the signal will be higher. But really, just I think it more comes down to the idea that when the stars, that you want them to be small enough that you're resolving them on, say, the baselines of these Cherenkov telescope arrays, but you also need them to be very bright. And so hotter stars are of course going to be a little bit larger, or much larger. And but then again, that means they're going to be much further away. They're also much rarer, so they're going to have different distances. And essentially, there's a nice overlap between the array geometry and baselines with these bright hot stars, which are their size is matched well to the baselines.
Gotcha. So this thing with like the Betelgeuse releasing this cloud that made it super dim, mm-hmm. That's something that's not possible to do right now with the system, but maybe with more advances, you'd be able to see this kind of activity on the.
So with Betelgeuse, I think it's the size. So Betelgeuse is, I think, 40 milliarcseconds or something in size. And so you only need a baseline of a few meters, if I recall correctly, to actually resolve it. Or I guess Michelson did with his original 20-foot interferometer, is that you only need, getting my thoughts confused, but yeah, so you only need a few meters, whereas these telescopes are separated by distances of like hundreds of meters. And so they're actually, Betelgeuse would be a little too resolved to be able to see those features. And that's where amplitude interferometry, I think, does a better job, is with these much, much larger stars.
Okay, that
want to access
sense.
Higher resolution and smaller stars, intensity interferometry is a nice approach.
So Tugdual says, I nightmared it. Nolan did it. It's an extremely difficult measurement to do. And I think he was referring to the resolution of these stars. Is that right?
I nightmared it. I'm not sure. Can you read that back to me?
He says, I nightmared it. I think he meant like dreamt it, but it was a nightmare for him.
Okay.
And then you accomplished it, basically.
Yeah. I guess I don't know exactly what he was referring to, but I guess, I helped lead the construction of the actual instrument that worked with VERITAS. Maybe that's what he's referring to.
I think so. It came in a little bit ago, so I'm not, like 3 minutes ago, so I'm not exactly sure exactly what part he was talking about, but I thought it was kind of a funny comment because he nightmared it.
I shared a lot of struggles trying to get this stuff to work in the laboratory, so I know the pain that he's felt as well.
Yeah, you guys spent a lot of time trying to figure that out, I remember. So we talked basically about the physical parameters. We talked about that. So could you explain how you rebuild the signal back into like showing what or determining a stellar diameter or something? Like how you take the data and pull it back into something that looks like a...
Yeah, so I'll start simple here and go back to this slide. Again, the idea is that you want many different telescopes at different baselines. You correlate the starlight intensity at many baselines, and using that information, essentially how correlated are those two streams as a function of the separation between them, you can actually have some sort of model for the star that approaches it. And so I guess the interesting is, how does this model work? In that what you see is that for example, for a particular star, it's going to fall off. The correlation with some distance is going to fall off based on the size of the star. Very small stars will maintain their correlation over large baselines, whereas very large stars, the correlation will die very quickly. And so essentially what you want to do is measure this change over some range, which is appreciable, in which the change is appreciable. And from that model, you can kind of get back the stellar diameter. But the way you actually form this model is from a more kind of complicated thing. The idea of how does the information you obtain relate back to the image of the star. And so what we measure in intensity interferometry are visibilities, essentially the modulus of the visibility to be accurate. But essentially by measuring the visibilities over many different points, you can essentially do what's called an inverse Fourier transform and get back what the source was originally, the brightness distribution of the source in the sky. And so I actually show here on the right, I try to make this a little more illustrative, is that say you had some star, which we describe in astronomy. The most basic model for a star is something called a uniform disk. You say it's some size in the sky and it has a flat uniform intensity across the surface. Now, if I was to take the Fourier transform of this star, I'm going to get this pattern here. So what the intensity interferometer does is measure these visibilities at many, many different points. Each pair of telescopes gives you one point in this kind of image here. And then by measuring over many, many different points, you can kind of do an inverse Fourier transform and get back the size. But again, like if you had a very small star, if this was much smaller, the extent at which this first kind of circular ring extends would go much, much larger. And so again, by measuring this kind of information many times. So whereas, this is for a single star, you can imagine a situation for a binary. And for a binary star, the Fourier transform looks like this, which is kind of like this one, but you have this modulation across the same direction at which the two components are located. And this modulation is directly related to that. So if you've ever done the double slit experiment, say in optics, this is the same kind of idea. And again, by measuring this modulation over this pattern over many different points, by correlating between many different telescopes, you can do an inverse Fourier transform and get back the distance between the components and the sizes themselves. And this last one here is again, just the binary, now it's moved in its orbit a little bit, and now the modulation is along a different direction. And because they're farther apart, this modulation frequency has increased.
So just looking at this, would you be able to determine the orbital period of these stars in a binary system just by looking at the shifting and modulation?
So I think the orbital period is best determined through photometry, because you can get much more precise in terms. You see this periodic modulation in the light intensity over some time. But what's interesting is the exact parameters of the orbit. Is it orbiting like this? Is it going like this? And what's the inclination and all these other things? And that's where having high resolution information is really important. And that's where I think that, for example, with there's a Spica was the binary study originally by Hanbury Brown. And with that, they were able to extract a ton of stellar parameters, the individual sizes of each of the stars, the inclination, various orbital parameters. And they did this with interferometry. And actually I have a GIF that this is credit to Jason Oftenberg. This is of Spica, where he has a full model of, for example, of the Spica system, which is a really interesting binary system, which they orbit. It's two components, two really B spectral type stars, which has a 4-day orbit. So these two stars orbit each other every 4 days, and there's a lot of interesting effects going on. For example, when one of the components gets closer to the star, it actually, the effects of gravity cause one of the stars to become elongated. And so there's all these interesting.
Yeah, I was just going to ask about that. I see it kind of turns into an egg shape when it gets to the bottom left.
And that's a real.
So I was wondering if that was just something from the animation or is that something they're.
And so Jason is a really brilliant guy, and he has this very nice model of this system with tons of data on it. And this animation is based on his model parameters. And so beyond just the gravitational elongation of that occurs when this orbit is happening, you also get effects when the stars get closer to each other. They start irradiating each other. Essentially, one star lights up the other one, and you can get variations in the brightness just from that kind of feedback. And the last point
I can see this.
The scale of this is on the milli-arcsecond scale. And again, you need to see this system to actually get these individual components you need interferometry.
So I was kind of wondering, so once you're able to do this, kind of in a more robust way, where you can do it over and over easily, this is going to help things like stellar evolution models, stuff like that, brightness models, size models, and stuff like that for other astronomy people out there too. So it's not just looking at a stellar diameter is like a lot of other things that can come from that to either help refine other models on star formation and stars evolution and stuff like that, right?
Exactly. Yeah. The main goal is to, I think I forget which paper it's in, but the idea is that when you get this higher resolution information about stars, these fundamental questions about the stellar evolution and stellar modeling and the atmospheres of stars, and I think interferometry is a core tool and has been for some time now used to probe these understanding of stellar physics. And of course, like as you say, stars, they're used everywhere in astronomy, from understanding distances to galaxies, just to locally understanding our own solar system. Stars are of fundamental importance.
Yeah, so like if you could like look at something like Deneb and actually determine a stellar size for that, that would help you kind of maybe pin down the mass and the brightness a little bit more, because there's like a huge error in the distance of that because of stellar or interstellar dust and stuff like that. So if you can pin down some of these other parameters using this, then you can kind of get a better idea of how interstellar dust is causing differences for, or causing problems for, like determination of stars like that, right?
Oh, no, that's interesting. I haven't thought about that, but I think you're right in that, it's a lot of times stellar diameters, they're inferred from spectroscopic models and things, when you're using just the spectrum of the star, if there's effects like dust and maybe just variation in the stars, like you can have these systematic effects which propagate down to other fields and somewhat, whereas interferometry is a direct measurement of the diameter, and you can use this direct measurement from interferometry to check the spectroscopic model, which can be used on many more stars. Many more stars are, of course, accessible from spectroscopy, but these constraints from interferometry have and still are being used to constrain these spectroscopic models. And that's
cool.
Actually,
what were you going to show us
here which I'm showing an HR diagram of the brightness, the intrinsic luminosity of the star as a function of the temperature. And of course, this is a fundamental tool in astronomy to understand stellar evolution. But this HR diagram was actually formed from purely direct interferometric measurements, whereas the size of the circle here indicates the kind of roughly to the actual size of the star. And what you want is these direct measurements over a huge swath of stars, so that you can constrain then the HR diagram models, HR diagrams that are formed from spectroscopic surveys.
I really like that. I've never seen a HR diagram built off of stellar diameters before.
Yeah, it's a cool thing.
That's pretty cool.
I mean, and it's only in the last decade or two that they've been able to form a large enough collection of stars to do this. And so, and this is actually interesting, is that what you see is that it's really well populated for lower temperature stars, but there's kind of discontinuities and breaks at higher temperature stars. And that's simply because amplitude interferometers, where almost all of these results are formed, except for the hottest ones, which were formed from the narrowbody intensity interferometer, were formed with amplitude interferometry, which is better at characterizing these larger but lower temperature stars. And so an avenue for intensity interferometry, in my opinion, is to study these hottest stars with increased resolution and constrain kind of the HR diagram on here. The other reason why it's a little bit, there's breaks here, simply that these hottest stars are the most rare. And because there's only a few of them, to get a large number of them, you have to go to great distances, in which case they're going to be really small and you need huge baselines. So again, back to why you need intensity interferometry. Hopefully.
Yeah, that's cool. You'll be able to fill in the rest of this graph with your research. That's pretty cool.
That's the idea.
Let's see. So we kind of did that, talked about that. So let's talk about what are the current limitations that you're coming across. Like, is it electronic limitations? Is it baselines? What kind of stuff is keeping you from going farther so you can get better results?
Right. So there's a few things. I think experimentally, a long time we were limited by noise. This is kind of an annoying thing to talk about, but any person who's working in science knows that, the signal, what you're looking for is easy to look for, but the noise is always the issue. And so in our case, it's because we work at high frequency and we digitize the starlight at megahertz frequencies, which overlaps with the radio band. And so we get influenced, if there's a radio transmitter at the site, we pick up those radio signals. and they get into our electronics.
That's purely
go ahead.
Purely into your electronics, not into any other thing. So it's like leakage into your computing system, right? Is what you're talking about with that?
So like
EF, RF, EF problem?
The way to think about it, the way I describe it is that like one explanation is that at the anode, where the current exits the folded multiplier tube, there's a little metal wire, and that little metal wire acts as an antenna. And so if that little metal wire, which is transmitting the starlight intensity as a current, if it picks up some radio radio wave signal from, say, a broadcaster, from Border Patrol, from something, it's going to show it. It's going to pick it up as a high frequency signal, and we see that correlation in our pattern. But we're getting around that both by just improving the shielding. Anybody who's worked on electronics, so you can kind of shield out radio waves. And also we've been coming up with kind of nice ways of kind of removing the data post observation. So so that's the main thing with the noise. But I think we're getting around those practical limitations. Fundamentally, you still have to increase your sensitivity. You need higher efficiency detectors. You want larger mirrors, and so right now we're restricted with the size of the mirror. So in like various upgrades that we're thinking about improving the efficiency of the detectors, essentially improving how well they collect the light and turn it into a current, as well as improving the time resolution of the detectors. And so currently those I think are the limitations, is improving the kind of how much light we can collect we can't really change the size of the mirrors, at least at VERITAS, but we can try to improve the efficiency at which we collect them.
So there's not anything that's like holding you back that's like not technologically possible right now. It's just getting better electronics, better, bigger things.
I think
there's not anything like theoretically that is problematic here that is causing any problem.
So no, I wouldn't say theoretical. It's more practical things that we're forming a better and better ideas as we learn from this instrument about ways to improve it and push it forward. One of the things that we would like to do is to observe. Like right now we observe with a single narrowband filter. So we observe light at 416 nanometers with a filter that's about 8 nanometers wide. Really more like 10 to 12 nanometers wide when you compensate for optics effects. But anyways, so we have a single band. What we'd like to do is observe in many different bands simultaneously. And the idea is that, the star is different at different wavelengths. And so you're probing effects of the star at these different wavelengths and understanding how they correlate with each other. But also is that the signal noise, you could actually combine all those independent measurements and co-add them together and get a stronger signal. But the problem there is the fact that these Cherenkov telescopes, because of their reduced optical quality, say compared to like conventional optical telescopes, it makes this filtering into different spectral bands really challenging. So it's like
a chromatic aberration problem.
I think your mic
like a chromatic aberration
problem. I can't hear you.
Did it go stupid again? Can you hear me now?
I can't hear you. I don't know if others can. I don't know if others can hear me.
Oh, here we go. For some reason, my mic keeps turning down its volume.
Okay, no problem.
So anyway, is it like a chromatic aberration problem where you have all these different wavelengths at kind of basically different focal points and stuff, and so you'd have to change the system ever so slightly, or is it
more geometrical? I mean, it comes down to, like I said, the PSF of the telescope is 0.06 degrees or 0.1 degrees, right? And that's, the stellar image, when you look at the focal plane, is literally like that big. And to the other problem is that the light is coming in at a very big angle from the mirrors. So if you essentially light comes in at a sharp angle and it's focused to a very large spot, to filter the light, you need the light to go straight. But the problem is that to collimate the light, you're going to need a huge lens because of this large PSF to collimate it. And then you're talking about really expensive optics. And it becomes more challenging to break it into different bands. So it's really the optics of the geometrical optics of the telescope that limit it.
So like you would need to do that. And then is there a possible way you could put like different photomultiplier tubes next to each other with different filters on them?
Yeah.
And have the light coming all onto them at once? Is that like one of the solutions?
That's an idea, but again, to filter light, you have to start breaking it into different paths. this big PSF and fast focal ratio, it's just challenging with shrink-up telescopes. Now with optical telescopes, PSF, is on the scale of potentially 100 microns or something, and then you can use 1-inch optics and other things, and you can of course use a prism or just something else to break the light up. But that's really hard to do with shrink-up telescopes.
So it'd be like you ideally want an interferometer that is also a spectrometer.
Exactly.
Gotcha.
Things.
Yeah, Tug DeWall came back and put up another message. He said Nolan did something that had not been done in 50 years and that no one knew how to do. That is what he meant. It's a true achievement. So he's just giving you some great praise there. So.
Yeah. No, I mean, and so maybe speaking broader, like when I got into my thesis project, at the time, I was kind of naive. I mean, I just thought it was a cool project, and I was like, I'll just keep working on it. But no one else had done this from the time of Narrabri, from Hanbury Brown. And now there's, I think, probably 5 or 6 different groups worldwide that are now pursuing this technique. And so I think, it is, something I'm proud of is that when I went into this field, there wasn't much of a history to it, and at least modern history is what I should say. And so a lot of the things we did were kind of just unknown, and we developed a lot of techniques that we kind of had to push forward without knowing if they'd work or not. But I think that, as a lesson to say budding physics and astronomy students, it's good. It's kind of very rewarding. It might be more challenging, but it's very rewarding to push into something that maybe doesn't have a very strong history or is somewhat unknown.
Yeah. Well, you're a pioneer now, right?
I don't know.
Okay. Let's see. I think we got through like the whole idea of like what we were doing there. We actually even talked about that one. So we talked a little bit about how it'll help in astronomy. What are like some things that you can immediately think of, like in the now of what it could produce for astronomy? Like, are there things that could be like taken up right now within the next 2 or 3 years based on what you have already set up?
Yeah.
To start getting data out there. Yeah. What are those?
So one of the aspects I haven't touched on is that we can observe at blue wavelengths. So we observe at around 416 nanometers, whereas most interferometers are restricted to like 500, 550 nanometers plus. And so we're actually probing the star at wavelengths which are not currently accessible. And so I think that's a big benefit because, say, one example, and then you can go down many different avenues of why this is useful, is that one avenue is that you measure a star at 2 different wavelengths. You measure it, say, in the red at, say, like 700, 800 nanometers, or you measure it in the blue. And you can have a model which predicts the diameter based on some model of the atmosphere of the star. And what they found is that as you push to shorter and shorter wavelength, these models at short wavelengths don't necessarily agree with those at longer wavelengths. And so there's some interesting ideas about, what's going on in the atmosphere of the star. Is this linked to the physics of the star? And it probes the atmosphere of the star as well. So I think that's something is that we're now, just with diameter measurements, we're providing a space of interferometry at very short wavelengths. And that's useful for the things I've said. The other thing is that, because we work in arrays of telescope, it allows us to characterize, somewhat these exotic stars, which we call rapid rotating stars. And these are stars that are rotating so rapidly that they actually bulge out at the equatorial region. And these are just, really interesting stars. They just, completely perturb the shape of the stars. And because the gravity at the equatorial region, the effective gravity is near zero, it's actually shedding material as well. And these are the progenitors of supernova, which eventually lead to neutron stars and black holes. And so they're just interesting environments. If you want to study the environments of supernova, pre-supernova events, these massive stars are where you want to go. And rapidly rotating stars are something that I think intensive interferometry is really well suited for.
Yeah, that's cool. I think you had some slides showing some of those.
Yeah,
you want to pop one of those up real quick, just to give an idea of what that kind of is for some people.
Should be sharing now. And so this is something that's currently being studied with current interferometers, and these are actual image reconstructions of these stars, of these rapidly rotating stars. And again, because they're rotating so rapidly, they bulge out significantly around the equator, where you see here along the polar axis. It's much shorter than the equatorial region. And they've done this for a few different stars, and they're showing they kind of also they overlay it with the latitude and longitude kind of images to kind of give you a better idea of what you're looking at. The other thing with these stars that is kind of interesting is that because there's this difference, there's actually a temperature gradient. Essentially, the polar region is much closer to the core of the star than the equator region. And so you should expect to see a temperature gradient as you move from the pole to the equator. That's known as the von Zeipel effect. And most of these stars are B-type stars, very, very hot, very massive. And again, that's an area where intensity interferometry overlaps. But to study them at many different, say, scales, not just along one axis, but many different axes, you need many different telescopes working in combination.
That's cool. Because, yeah, I learned about those kind of things a while back, but it's always interesting to keep hearing about, stars that are rotating so quickly. And like if they do go supernova, those are going to turn into like neutron stars that are like the rapidly rotating neutron stars that could potentially be pulsars later on with like super high pulse rates and stuff like that. So it's interesting to think about that. Do you have another one here? Is talking about the expansion of nova ejecta? Is that something that's something?
I found this to be. I think this is more suited for amplitude interferometers because the temperature is much lower. But regardless, it's I think a really cool thing, demonstration of what high resolution capabilities get you. And so this was a nova from 2013 that was observed with Chara, I believe. And essentially over the period of a few days, they were actually able to record the change in the angular diameter of the star. Which is shown here in the plot, where the angular diameter in milliarc seconds and the time in days, and you can actually see this nova ejecta start to expand, which is just, I think, a fascinating way to look at these nova.
Yeah, that'd be really cool to be able to see something like that.
And then you compare these images along with the photometry. And
and then see like any resulting stuff that comes on like 5 years down the road or something like that, like a planetary nebula type thing that's going on out there. All right, let me look at. I think we're getting pretty close to the end. We're over an hour, so let's see. So I got one more question here, and it's basically just, what are your personal goals and maybe your career track? Is it going to continue in this for the next while?
Yeah.
What are your personal goals with this project? And
so this particular project, I'd like to stay involved, but and continue to push it. I think we've brought it from something that was unknown if it could even work into an instrument that we're somewhat routinely observing stars with VERITAS, and so I'd like to continue to push it and see where we can take it and explore these scientific possibilities that we just talked about. For me personally, I've taken a postdoc position in southern France. With actually a quantum optics group who has realized that their stuff that they use in the laboratory in quantum optics is also intensity interferometry can be used for stars, and they've successfully used intensity interferometry with optical telescopes. And so I'll be joining them in working with their setup and furthering their setup towards the use of intensity interferometry with optical telescopes instead of Cherenkov telescopes. So the long-term goal is to continue to push this. I mean, I have visions and fantasies of pushing down to very faint magnitudes and observing very subtle effects. I think there's a lot of interesting stuff that you can do, especially with optical telescopes, and really start to get to exploring these stars at very high resolution and understanding them more. So yeah, and that is academic. I'd like to stay on the academic track, so I'll do that postdoc appointment for 2 years, and if all goes well, I'll continue to search for academic positions. Of course, it's very challenging, but I think the tools and things I've learned will set me in a good path no matter what I end up choosing to do.
Sounds like you'll be probably going towards places where they have large shrink-off detectors, right?
I mean, that's a possibility, yeah. And so CTA, for example, is a future array. It's currently being built, and there's an active working group that's trying to do intensity interferometry with CTA, and that's another dream is you can outfit up to 50 telescopes with intensity interferometry capabilities. You can really do new things with it, and that's absolutely an avenue I can continue to explore.
we have a question that's just asking: is there an estimate for the linear distance for the angular size of the Nova that was on your slide?
Linear distance. I wish I knew. I don't know what the distance is. You can try looking into that. This is Schaefer et al. 2014, and this unit here is in angular diameters. So if you look up the linear distance, which is probably on Wikipedia for this Nova Del star, you can then convert that to a physical thing. But so, if we're thinking about a solar type star, I mean, you're just seeing it increase by a factor of 10 in about a month period. So these are massive, massive scales, like solar system size scales, I would assume, that this is occurring over. But I would say, yeah, look into the details. I don't have a linear estimate off the top of my head. It's a good question.
I did have one other question, and that was something I was reading while I was kind of researching the background on this. And it was talking about the basically the angular view of the shrink-off telescopes is like extremely wide. So like VERITAS has like a really wide angle of view, field of view. How is that problematic for what you're trying to do when you're looking at very, very small fields of view?
So I don't think the field of view matters so much, because if we go back, I guess I'm still sharing my screen. I skipped it. That wild field of view, and it's kind of hard to see here, but you can see the gamma ray camera behind this black plate here. That field of view is granted by the camera. It has pixels that extend all the way out there, and whereas we're just using a single pixel. And so maybe the optics, the design that went into the optics, wanted this wild field of view, and you compromise, for example, some of the PSF for a single pixel. But I don't think it has so much effect. The real problem is that because you have this huge PSF, which it integrates a lot of the background light. And so eventually, once you get to very faint stars, something like faint, I mean, faint is a relative term, but for interferometry, faint is anything less than magnitude 8 or something. Once you get to those type of stars, then you have a problem of you're integrating too much night sky background light into your detector along with your starlight. And so that's where the limitations, I think, from shrink-off telescopes eventually lead. And that's where optical telescopes, if you can build intensity interferometry that can push the magnitude limits, they're not as constrained because the PSF is so much better.
Okay, yeah, that makes a lot of sense. So is there anything else you want to add? Because that we kind of made it through all of the questions and stuff that we kind of had before.
In particular, thanks for having me on here, Paul. Let me talk about this, and then also thanks to Dave Gita, my advisor, Tugdualabug, who's been essential in guiding me to where we are now, and as well as many undergraduates and other people I've worked alongside with.
Yeah, well, thanks for doing this too, because I've always found it really interesting, but I never really got super involved with it at all. Right. But I know Tugdual's been working on it for a while, and it's and you had to borrow our truck a bunch of times to get out there. Times for
Starbase.
Yeah,
I should have said that. Thanks to these.
Oh yeah, no problem.
For letting us borrow the truck.
Yeah. Thanks for doing this. I'm sure everybody who was on, we didn't have a ton of people on, but those who were on, hopefully they had a good experience. And if it's okay with you, I usually post these onto YouTube for other people to watch on there also. So get some more people involved with that maybe there, and some brighter minds for to help you out later when they get into college and you're a professor working on this somewhere. Mm-hmm. So yeah, thanks again for doing this. And if nobody else has any questions, we'll give it a minute to take any more questions. But yeah, it was fun. This one was really interesting for me. Robert says thanks. Tugdual says great, thank you. And yeah, I hope you actually have a good time in the next little bit while you're traveling around the country a little, and then off to France for a couple of years. Mm-hmm. It sounds like a really fun endeavor that you're going towards.
Yeah, I guess
yeah. It's an interesting.
It'll be a journey.
Switch
for sure. Mm-hmm. Exciting one though.
Yeah. Do you speak French?
I do not, just a little bit. Been trying.
I think a lot of the French people speak English, so you're probably
Yeah,
good.
I'm gonna learn for sure.
Yeah. Have Tug the Wall give you some lessons before you take off. Be like, hey, what are some of the basic things I need to know so I don't end up in a trash can somewhere?
Yeah, that's very. I've hopefully learned enough the basics to get around, but
Yeah.
sure, I'll hopefully learn more much quicker when I'm there, just via immersion.
Tug the Wall says, Ma wall, what is that? May ou bensur? I don't, bensur? I don't know. I can't read or speak French, so you might have to get him to translate that to you in person. Sorry, Tug the Wall. I murdered your language.
Yeah, I don't know what you said.
I don't know either. All right. Oh, he said apparently it means yes, of course. May we? I don't know. I'm trying to think of the things I've heard in my life, and none of them are working. All right. Seems like there's no questions, so I think we can just end it here. So I'm going to end the live video. Thanks everyone for coming. Hope you enjoyed it. Watch out for our future talks and stuff. Hopefully we'll be able to do more. A lot of people have very little time, so it's kind of difficult to get these. But yeah, thanks everyone on Facebook and stuff. So enjoy the rest of your night.
All right.
Goodbye.
Thanks again.
Yep.